and welcome to this webinar from ATA Engineering, talking about the latest version of STAR-CCM Plus 2020. Just a few things about the Zoom meeting we're having. Everyone right now is muted, and at the end of the presentation, we'll unmute everybody for questions. I'll be talking a little bit about ATA and some of the new features, and then Chris Ostoich, one of our engineers from ATA, will be diving in a little more detail in some of the others. And so with that, we will press forward. If I can make things go. Here is a list of all the things that have been released in STAR-CCM Plus 2020, the total new features. And basically, we're not going to be talking about all of these today because the list is very lengthy and we don't have much time in terms of doing all of them. So we're going to just tackle a few of them. We're going to be tackling those 3, 4, 5, and 6. By the way, I've just, in the nick of time, some leaf-blowing landscape people have started outside my window. So if anybody can't hear me or it becomes painful, please send me a note on the chat. So this is what we're talking about today. But before we do that, let's just dive in a little bit into ATA Engineering for those who don't know who we are. We are an employee-owned company. Around 150, and really we are consulting engineers with a very high skill set of members, basically 14 professional engineers, and as you can see, a lot of PhDs, a lot of masters, educated engineers, and really focus on very high-end engineering for consulting projects. Our market varies from aerospace and defense is our primary one, but robotics and control is another big area. But theme entertainment and mining is also new markets for us that we're pushing into. Now, a lot of people are kind of not familiar with ATA. A lot of people on this line might be, as some of you I know are customers. But just a very quick note about the history. ATA used to be basically the testing division of SDRC back in the 70s and 80s, and really became ATA when STRC was transitioning from an overall engineering company to a software company. And so in 2000, ATA Engineering was created out of STRC and has slowly grown to the organization that it is today. And really, in the last 5 years, we've really especially become much bigger in the support of Siemens tools, especially STAR-CCM Plus, but we also sell and support many others, particularly in the Simcenter product lineup from Siemens, but on many others as well. And so on the services side, our main focus is on analyst and test-driven design, and we really, focus on the toughest engineering challenges, basically from ground vibration tests to state-of-the-art aircraft flight tests, things like that. And all along, we're using Siemens tools as well. So not only do we sell Siemens tools, but we support them really through our own use and our own expertise, passing that knowledge on to our clients. And really, Chris is a perfect example of that, doing a lot of projects using STAR-CCM Plus. And so we have offices throughout the US, and really only in the US, but you can see a lot of them are in the aerospace centers of the country. I'm actually in Boston today, but I know a lot of you are probably working from home with the COVID-19 issues, and I hope everybody is well, but we're scattered across the country, and most of ATA are working from home as well right now. So let's move on to STAR-CCM Plus itself. And the new version of STAR basically has a lot of amazing features that we'll be covering some of those basic ones today. But this is just some eye candy to get people started on some of the new things that it can do. And I know some of you may have seen this before, but some of you may have not. So I'm going on to basically, what we're going to talk about today. Really, I've removed the other items, and the 3 features we're going to talk about today is adaptive mesh refinement, the new poly mesher, and basically the new automated coupled solver control. Really, the first 2 are the main things that we have used at ATA, and so we can give you more kind of insight into our use of that. as well as the Siemens information that we've got. So when you look at adaptive mesh refinement, it's kind of something that it's been the holy grail, if you like, of CFD for a long time. These noises outside are getting worse, so again, let me know if it becomes prohibitively noisy. But basically, adaptive mesh refinement is something that people have been chasing, and STAR hasn't had to do it before. I'll talk about it a little in a minute, but really just using JavaScript to do remeshing. But the new adaptive mesh refinement is really much more advanced than that and much easier to use. And so I know that most of the people on the line are already, STAR users, and so a lot of these are going to be obvious. But what's the benefits of adaptive mesh refinement? And obviously, cutting down the computational time, but yielding the same accuracy, and also reducing the manual meshing time that you need to build this perfect mesh at the outset of a simulation, when really the solution can home in on it as you go along. It has a lot of benefits that make life a lot easier. And then, which areas of application can it be deployed in? Obviously, steady state and transient simulations is important. And also the mesh types in STAR, polyhedral and trimmed, really the main mesh types that everybody uses, the others, TETs, and some of those others, not many people use anymore. And also, pretty much most of the physics, VOF for multi-phase with free surface, overset meshes, and also if you want to adapt with your own coding and your own user functions, you can do that too. The other thing that Chris is going to talk about later is that the new mesher and the enhancements in the parallel processing nature of that. And obviously this connects to that, in that if you're going to be doing remeshing during the runtime, one question everyone has is, how's that going to impact runtime? And so basically maintaining that connection with the parallel processing and making it utilize the hardware you've got as best it can is very important, and the new AMR system does do that. And so this is especially useful for free surface meshing, and this has some animations. Let me kick those off while it's thinking. And so, the great thing about doing a free surface model with VOF is that it can actually refine the mesh density around the free surface interface. And that's really important when doing really any of these models, because being able to actually keep the mesh density down but get enough mesh density at the VOF boundary is often a challenge. And so, basically you can get the fine mesh where you need it, and it works with all of the multi-phase approaches, so that really you can use it in any application. And once again, it really makes it easier to not have to spend loads of time at the beginning dialing in your mesh to really match where you expect the free surface to be, because it's going to tell you where it's going to kind of calculate where it's going to be. And so one of the nice things it does, it actually refines, it projects where the free surface is going to be going and modifies the mesh in front of that. And obviously on the back of that too, where it's been. And so it's kind of an intelligent remesher, and it predicts where it's going to need new cells and gives you that ability. So it's pretty strong, and really, with older free surface models, really STAR has been at the forefront of marine modeling and free surfaces for a long time. But that interface of the VOF interface was always a little bit smeared because of the mesh density at the interface. Whereas this now lets you really define sharply the fluid interface without going crazy on mesh density. And not only that, it can also be used in overset mesh applications. And so, especially again on the marine side, this has some animations too. We'll run them both. But certainly, look, when you're doing the first one, when you're looking at an interlocking geometry problem, as the geometry comes close together, in the past, you needed to project where that connection might be and build enough mesh appropriately. But now you can do that on the fly and let the AMR system give you extra mesh, when it needs to. Not only saving you a huge amount of time when you're preparing, but also just reducing the cell count by a huge amount, because you don't need to add cells, throughout the whole domain. You can do it only when the contact is close. And so, as you can see in this example, Siemens talk about a ×10 reduction in cell count, which you can easily believe. And then when you're looking at free surface hulls, modeling, especially planing hulls in water, the normal MO has always been have the water and the free surface of the ocean or the sea in the background geometry at a flat level. And then the ship or the boat was always in an overset mesh region that was allowed to rotate and move around on the free surface. And so in order to do that properly with the new method, obviously it's got to be compatible with overset meshing, which it is. And so if we run this again, you can see that this example here shows the overset mesh of the boat moving through the background mesh, and also the new AMR capturing all of a much better fidelity level of the free surface without smearing. And then another extension of that, if we keep going, let me run these animations while we're. The other thing that's nice is that the initial mesh can be much smaller, because if you know it's going to refine in the areas of interest, you don't need to lose so much sleep that you have this fantastic mesh out of the gate. And so, that's a huge advantage. And also, you can combine how you adapt the mesh too. If you want to do it on multi-phase VOF, say, you can do that. If you want to do it on other things, and also a blend of those. And so an example that Chris is going to show later is Mach number to capture a shock. But really, you can choose what you refine the mesh on, which is clearly pretty powerful. This one's a shock example. We'll let it play while we're talking. And so sadly, life isn't perfect, as we all know, and there are a few limitations, but they're not too bad. One of them is that the mesh that gets redone is basically refined to tessellation is not projected back to the CAD. So if you want to extract a new surface geometry for the CAD, as yet it can't do that. I suspect it will do in the future, but right now it can't quite. And you can see the list on the right there. I won't read them all out because you can see them, but it's not compatible with all of those physics pieces yet. But as time moves along, I'm sure all of those will be added to the list of things it can cope with. And so I just want to revert back a little bit. We did a webinar about 6 months ago talking about mesh refinement using JavaScript. And so we actually have a case of a projectile, and this is taken from that webinar. And it talks about how you could do mesh refinement before. And if you look at this Java, you can see basically it assesses a new mesh size based on a field function, and then it basically does a remesh, a full remesh of the whole domain. And then it runs through the loop again. And that gave, if you were trying to track a shock, that worked very well, but it was very inefficient because it was doing, maybe during the course of the process, it did 10 mesh executions or whatever you set it to do. Obviously not very efficient, but did work. And so in terms of so this is how the older version would work, in just doing a pure remesh at a certain number of time steps to home in on the Mach number. So the new version is really so much better than that, because it basically does cell splitting of the initial mesh. And so it's not really doing a full remesh during the whole solution. It's really, in fact, it's just doing cell splitting and then removing that split as it needs to. So it's not doing a full remesh at every time step. It's just doing a cell split when it deems appropriate. And so it's so much faster than this. And so you don't get this huge overhead in remeshing, like I'm sure everybody would be concerned about, is adding to my time for solution. And so really, this slide from Siemens highlights the idea how easy it is to add to really any model. It's part of the GUI. Basically, you can set all of the criteria in the GUI from coarsening and so forth. You can set the minimum adaptation cell size and also the maximum refinement level. And so you can, it's really it's a standard deployment within the STAR-CCM Plus environment. Very simple, very straightforward. No JavaScript, as in that previous example, and super efficient. And so these are a few examples of basically using it in a model where perhaps an old model has been used, and comparing how much it improves things. So in this example, this is a pretty intense problem for STAR, really, for any CFD code. Oil in gears moving. It's got moving geometry, It's got multi-phase if we can make it do what we want. And it's just pretty extreme. And so the original mesh here was a 90 million mesh and then ran for 300 hours on 216 cores, which for pretty much everyone here, you can imagine that's an intense problem. But converting it to AMR meant that you didn't have to have all of that mesh that was, for the most part, unnecessary for most of the simulation. So it was cut down to 9 million cells and ran to 50 hours. And so, all of us, I think, can see that this is a huge improvement and one that we'll be able to see for really all our models. And then this is a slightly different application, but it's still interesting, and that is that this is the NHL-20 re-entry vehicle, and it's coming in at kind of Mach 10. And really, in this case, this is an example of using Design Manager to actually run through a parametric sweep of angle of attack from -10 to 30 degrees. And so, in that case, really, pretty much the model remains the same in all cases, and just the boundary conditions, so the angle of attack change. And so this is another time where, the shock is going to be in different places each time, and hence the mesh needs to track that. But in the past, this was tough to do. But now with the new AMR tool, you can really create a design sweep for parameter in a model that includes shock waves. If we let this kind of animate, you should be able to see. So remember, this is the running through a number of design sweeps. I'll bring up these next things. And also note here that you can see that this mesh is mostly not changing. Only the mesh within the region of the shock is changing. Let me play that again for you so you can see it. And so it just highlights how efficient the process is, and by only remeshing and cell splitting where it needs to. So again, a parametric sweep like this of a parameter lets you really do this again automatically and very quickly. And you can see that the prediction of the shock and everything else, and the drag coefficient was very close to experimental. It doesn't really tell us in this slide what it might have been in the previous version, but it's still a good capture. And then again, if you want to combine all of those things with pressure and mass and so forth, as well as with an overset mesh model and DFBI, dynamic forces for bodies, this is an example of really combining kind of everything. So, it's a delta rocket stage separation, it's hypersonic, the fuel tanks are jettisoning and going through the shock wave from the main body. It's kind of a nightmare scenario for CFD, but using the new system does a really good job of letting you do it firstly, and secondly, doing it very efficiently. And then again, another VOF model, and this kind of highlights the idea that the AMR will track the free surface. If we run these animations, that one started, let's start that one too. You can see that this remeshing is happening here, and as it's moving, it's remeshing ahead of the interface. Super efficient, and really preserve that sharp interface without adding insane numbers of cells. So those of you who are doing marine applications or fuel and sloshing of liquids, this should be a huge help. And then really lastly, the idea of planing hulls. And this is really tight. Let me run the animation because it's pretty exciting. I think this animation really highlights how well the AMR can do at preserving the free surface and the droplets and so forth thrown off by a process like this. And secondly, make it easy to set up, because there's not really any steps to make it more challenging to set up. And not only that, the cell size can be dropped considerably, as you can see here, from the old method in last year using a big mesh of 4.5 million cells, probably only for half the domain because it's mirrored, to less than 1 million. So really does a good job of accelerating things, but keeping the results very robust. And then when we think about can we run different things to actually modify the mesh in different places, this is an example of that. We're using a propeller where the Q criteria for the vorticity off the tip of a propeller can be used as the AMR criteria. And again, you can see that we can pick up those really subtle swirls and vortices off the tip of a propeller without creating insane mesh counts to actually do that, which is how it would have to have been done before. So you can see that it's pretty exciting, and I hope all of you will go away today, itching to try this, and certainly Chris and ATA can help you do that. So with that, Chris, I'm going to pass it to you.
All right. Can you see my screen, Adam?
Yes, we're all good.
All right. Thank you very much. So I don't have leaf blowers outside, but you'll most likely hear my cat meowing and scratching at the door. She doesn't like being locked out, but yeah, I'm going to continue talking about some of the new features in STAR-CCM 20.1. I'd like to comment on the adaptive mesh refinement a little bit. One thing that I was excited about with this feature is the speed at which it operates. I was working on a problem a few months ago where I wanted to model the shock propagation down a wind tunnel during startup. So when a wind tunnel starts up, the filling chamber pressure builds up, and as the flow develops in the nozzle and test section, it is preceded by a transient shock. And so previously I built a very refined grid to refine the features of this shock as it traveled down the test section. But with this new feature, I just kind of wanted to play around and see if I could achieve the same effect of capturing the shock propagation, but with much fewer cells. And so this is kind of an example of that I'm showing. This is not the actual case that I was doing. It's just a little toy problem. And these results definitely aren't the final product, but it's just a demonstration of one application of how to use adaptive mesh refinement. So I'll now start talking about the new parallel mesher in STAR-CCM Plus. So here, I'll play this video. Is this playing correctly on your screen? Or is it a little
looks good. It's okay. A little jumpy, but it looks good.
Okay, so as our problems become more complicated and larger, we generate larger meshes, and so STAR-CCM Plus has come out with this new parallel mesher to generate these meshes more quickly in parallel and with better quality. So one challenge, again, is that meshing becomes a bottleneck due to the time required to generate very large meshes. The new mesher does this quickly, produces improved mesh quality, and has simplified user controls. So in the next few slides, I'll just give you some demonstrations of some of the speed up that you can achieve using the new mesher, and show you some ways in which the mesh quality is preserved by giving you a consistent mesh regardless of the core count used to mesh given geometry, giving you smoother growth rates between regions of high resolution to coarse resolution, and also there are no semi-structured meshes in areas of volume refinement. If you don't know what I'm talking about now, I'll give you an example in some of the future slides here. But if you look at the right plot on the right, you can see that the mesher scales pretty good up to, or actually very well. One of the success cases here is this 67 million cell grid, which meshed in 11 minutes on 256 cores versus 8 hours in serial. And then here we also have a 60 million cell grid, which meshed in 18.5 minutes on a little over 200 cores versus 9 hours in serial. Here's a case of, or an example of the mesher applied to helicopter aerodynamics. In this case, we see a 4.2 times speed up for 1.7 million cells on 30 cores. So this is a relatively small grid, but you still see a pretty good speed up as the number of cores increases. As I mentioned earlier, you get a consistent mesh. The change in cell count was less than 1/20% going from just meshing on one core versus 30 cores. And due to the fact that you achieve a higher quality mesh, you do get some improved convergence. And this is shown on in the plots on the right here. In 2019.3, as the solution approaches convergence, you see some oscillations in the aerodynamic qualities of drag and force here. In 2020.1, there are still some oscillations, but with reduced amplitude. And then here on the lower left, you can kind of get an idea of what I was talking about previously with the semi-structured region in areas of volume refinement. There's been, it looks like, a disk of volume refinement set up in the plane of the helicopter blades. And you can see that this is kind of, semi-structured. And the problem here is that at the boundaries of this volume refinement region, you get a large jump in cell volume and basically a non-smooth mesh. And this has been fixed in 2020.1. And you can see here in this plot meshing speed up versus number of cores, you get good speed up to about 20 cores on this relatively small problem. The next example is application to propeller in open water. Here we get 3.1 times speed up for 2.9 million cells on 30 cores. What I really want to point out here is, again, the much more smooth growth rate of the cells between volume refinements that you see in 2020.1 versus 2019.3. And this is really shown in the lower right-hand corner when you compare the two meshes. And then one additional feature of this new mesher is the simplified user controls. In 2019.3, there were a combination of 4 different parameters that needed to be set to kind of achieve the mesh that the user desired. This has been simplified so that now the user just sets the volume growth rate and the maximum cell size that they'd like to see. And the mesher takes care of the rest and ensures that the mesh has smoother growth from regions of high refinement to regions of coarse refinement. So I actually, a few months ago, ran into an issue using 2019.3 where I was working on a problem, and I noticed that there were that I could see processor boundaries in my volume mesh. So when I heard that this new mesher came out in 2020.1, which supposedly eliminated this problem, I was very interested. So I set up this toy problem here. And this is a zoomed in view or cropped view of a sphere in kind of a wind tunnel type geometry. And I've got a volume mesh set up around the sphere. So on the upper half of the slide, I meshed this geometry using 2019.3, and you can see that the processor boundaries are very evident. So depending on your monitor or how this is coming across in the Zoom meeting, you may not be able to see these processor boundaries due to the aliasing. But in a future slide, I'll show it from a view that makes it more apparent, but they're there. And actually, in the real problem that I was working on, these processor boundaries were giving me a real headache because that problem was a fluid structure interaction problem with the morphing mesh, and I kept getting some stability issues at those processor boundaries. Anyway, in this case here, I generated a 38 million cell polyhedral mesh. In 2019.3, the processor boundaries were evident, and it took around 118 minutes on 12 cores. When I remeshed this in 2020.1, the mesh then was 44 million cells, because the mesh controls between 2019.3 and 2020.1 aren't, apples to apples. But I wanted to generate a similar size mesh, so it was 44 million cells, and this mesh only took 63 minutes to generate on 12 cores. And furthermore, I can't see any processor boundaries, which was really exciting to me. So I basically got a higher quality mesh with a 216% speed up. So taking a closer look here, I'm just looking at the mesh that I generated in 2019.3. I mentioned before that I had that kind of volume custom control in this region. And I take a zoom in here, and you can see that we've got that semi-structured mesh, and there's what looks like some sort of irregularity here, where I kind of assumed there was a processor boundary. So when I plot the processor decomposition, you can actually see that assumption was correct, that this is the boundary between two processors. In the next slide here, I look at the same thing in 2020.1, and again, the processor boundaries are not evident. We get a more smooth and better quality mesh. Okay, and the final thing that I'm going to talk about is automatic control for the coupled solver. So the coupled solver is a very powerful tool, especially in problems where the momentum and energy equations are strongly coupled. But one issue is you oftentimes need to determine a proper CFL to achieve fast convergence, but also preserve stability. And so this can sometimes cause frustration if your simulation diverges and you have to restart it with a lower CFL. So in 2020.1, STAR-CCM Plus has come out with this automatic CFL algorithm. And this really just improves ease of use. It kind of replaces a previous kind of CFL control tool called the expert driver. And in comparison with that, it has reduced settings and user decisions. A lot of times you can just go with the defaults and get fast convergence. There's also no need for trial and error to find an optimal setup. It pretty much runs out of the box in most cases. It also improves robustness by, again, simplifying the setup and pretty much running without additional user input. So what it does is it automatically controls the CFL and under relaxation factors, and it's driven by an intelligent algorithm which uses line search optimization. The new layout for the user to interact with is very concise, and there's two main settings that the user adjusts. The user can use or can select a more aggressive approach by increasing the target algebraic multi-grid cycles, or improve the robustness by reducing the explicit under relaxation. So here is an example of this being used in an external aerodynamics case. In this case, some best practices for external aerodynamics with the expert driver have been established and used. So these settings for the expert driver have been set and tuned based on a lot of experience. However, when we use automatic CFL when we use the automatic CFL in 2020.1, we achieve actually more performance with kind of reduced user input or experience, again, just running with the defaults. In this case, we're applying this tool to a CHT analysis. So again, the expert driver needs tweaking in order to achieve the desired result, whereas the automatic CFL driver with the defaults results in faster convergence. And you can really see in these plots here that the expert driver is much more, it's a much more simple approach, and it kind of drives the CFL up to 200 and then tops out, whereas the automatic CFL is much more aggressive and reactive to what the solution is doing, driving the CFL number all the way up to 100,000 and then dropping it back to 10,000 kind of around iteration 240, depending on what the solution is doing. So it's a way to drive your solution to convergence faster with minimal user input. And then in final example is a natural convection example using a headlamp here. And in this case, you see a very large speed up using automatic CFL. And that's, again, just because it's much more reactive to the solution and drives the CFL and under relaxation to accelerate the solution to convergence. So that's all I've got for the parallel mesher and automatic CFL. Does anybody have any questions?
Thank you, Chris. Jonathan, can you unmute everyone for us?
Yes, so everyone should now be able to unmute yourself. You can do that with a button in the bottom left-hand corner of your screen. There should be a unmute button if you want to ask questions. You can also ask questions through the chat. And while you guys are unmuting or entering those chat questions, I'll go ahead and share that today's presentation was recorded, and we should have that video available on our software website and our YouTube page either this afternoon or tomorrow morning. But we'd be happy to take any questions now.
Okay, looks like William's unmuted himself.
Yeah, I had a question. So are there any plans, or are you aware of any plans that the thin mesher, where you can use it in parallel as well? Because now it's limited to serial, I believe. So if you have sheet metal, it kind of limits you. Just curious.
Yeah, I think we don't know the answer to that, William, but we'll go and find out from Siemens when they plan to include that in the parallel meshing.
Okay.
Anyone else got questions? It looks like most of the people on the line are users, so what I hope is that you'll go away after today and try all of these things out. So hopefully we'll get some questions on our support line during the next month. So we appreciate your time this afternoon. Thank you very much for attending, and everyone stay safe with the COVID-19 situation. And thanks again. Have a good afternoon. Bye-bye.